Okay, so last video we left off here. Reducing a force in a couple to a wrench. The previous slide we considered the case where the force and moment were perpendicular. Now what happens when they're not? So here we have the schematic. We have a force. We've reduced the system to a force and a moment. Gray is the moment. M perpendicular and M parallel are the moments perpendicular and parallel to the resultant moment. Parallel to F sub r and perpendicular to F sub r. When you have M parallel and F sub r, well, we can reduce that to F sub r acting at a single point to get this. Excuse me, I take that back. I misspoke. Remember when we had the perpendicular moment to the force? We can reduce that to this system right here. F sub r acting at point P. And we figured out where point P was earlier. Okay. Now we have a moment about point O and a force about point P. Remembering the couples are free vectors. We can move them wherever we want. We can replace this system with this. It's that simple. A moment acting at point P and a force acting at point P. That's called a wrench. A moment and a force acting at the same point. Okay. Okay, let's consider this. Replace this system by a resultant force and moment. Now you'll notice we have a moment. We have two forces here and a moment, and they're all three-dimensional. So I'm going to flip over to my Excel spreadsheet to make life a little easier. Okay, let's look at the Excel spreadsheet. So keeping the image in mind. Come on, Excel, where are you? There you are. Okay. So distance from ROC is 1 meter up, negative 800 newtons downward, acting along the z-axis. Moment is 0, and of course these are all divided by zeros. So let's go back, take a look. Is that right? 1 meter up, negative 800 down. So it's acting right on the z-axis at 1 meter up. Okay, so far so good. Negative 0.15 meters and 0.1 meters in the y direction, 1 meter up in the z. F2. Now magnitude 300 there. Let's look at the magnitude first. I had to calculate RBC to get the direction of F2. I needed the direction of F2, which would give me these three unit components of the unit vector. Let's take a look at the formula for F2. So you'll notice it's the magnitude times the first component, and this one's the magnitude times the second component. And of course this one's the magnitude times the third component. So that should be so far so good. The magnitude is 300, good. Negative 0.15 and 0.1 on the x and the y. X and y. So far so good. RBC, oh excuse me, here's RBC. 0 on the z. ROB, same x and y coordinates, it's just 1 up in the z-axis. So I had to use, for F2, I had to use RBC to find the components of F2. Found the magnitude. Okay, that's why this is standing all by its lonesome right here. So add up the forces. Just, there we go. Add them up to get the total F. And magnitude, or excuse me, total moment. This is the applied moment, not the total moment, not the total moment. The applied moment. Negative 400 in the Y, positive 300 in the J. Negative 400 in the Y direction, positive 300 in the Z direction. Negative 400 in the Y direction. So the moments created by these two forces plus an applied couple gives us the moment about point O. And let's get the force. And we got the force right here. And the moment. Total, that is not the total moment. That's the applied moment. This is the total moment right here. Okay, let's go back and take a look. So negative 800K, 300 UCB. This is, I calculated UCB in my spreadsheet. Got the same answer as this. M minus 400 plus 300 for the applied moment. Okay. And finally, add up all the forces. Negative 250, 166, negative 800. Negative 250, 166, negative 800. So far, so good. Total moment. Negative 166, negative 650, 300. Negative 166, negative 650, 300. Okay, so far, so good. Get the thing. It says the results are shown in 430. Oh, there it is. There it is. This is a schematic of the results. I thought that was the original. It is the results. They're shown in this figure. The idea going on. Now, of course, this can be replaced by a force and a couple, a wrench, in other words. But so far, we've got a moment. We'll have a moment parallel to the force and a moment perpendicular to the force. How do we get the moment parallel? That's the UAB dot this moment. Take that scalar times UAB again. That's the parallel moment to the axis of F. And then the perpendicular, of course, is this minus the parallel moment. Because the parallel plus the perpendicular moment will give us the total moment. Okay. Yeah, that's right. We're back here. And it goes too fast. Okay. Next topic. Distributed loads. They're all parallel forces, you'll notice. We have what's called a loading curve, this W sub x. And you take W sub x dx to get the force. dF equals dA. The area under this curve is the total force. Remember calculus, when you do an integration, you're getting the total area. Well, if F equals the area, F under the curve, F equals the area under the curve of W versus X. W is in newtons per meter. Then you can equate the integral W x dx, and somehow my L is supposed to be across the line, across this range of integration. It's just the area under that curve. The location, you'll notice this will be the moment. W of x dx is a force. This is a distance. So it's looking at the total moments going across here. And that is the total moment. And this is the total force. And if you remember, when we calculated the replacing a force in a moment with a single force acting at a single point if the moment and forces are perpendicular? Well, that's the case we have here. The moments are all going to be going off in the perpendicular to the force. So we can just pick, oh, what point over here will create that same moment, and replace a distributed force with a single force acting at x, at this x here. Location, x sub bar, actually x bar. We call it x bar. It's an average, x bar. Single force acting at a single point replaces a distributed force. Total force, of course, is just the area under the curve. Okay. So let's go to the next videos to take a look at a few distributed force problems.